This presentation will describe the jt8d-200 series engine fuel system. It will identify the system components, the component's function, the fuel flow path, and the permissible line maintenance adjustments. The function of the fuel system is to deliver filtered fuel at correct pressures and flow rates as necessary to meet all engine operating conditions. The components required to satisfy this function are a fuel pump, a fuel heater, and the fuel control. On the left side of the engine is a fuel flow transmitter. It is airframe supplied and is normally mounted here. Also on the left side are a fuel oil cooler and a pressurizing and dump valve, also called the P&D valve. Located in the diffuser case are the primary and secondary fuel manifolds and 9 of these fuel nozzles. The last component is the bleed valve control. It functions as part of the anti-surge bleed system, but it is controlled by a hydraulic fuel signal, which is generated by the fuel control. The aircraft fuel system is designed to supply fuel at approximately 20 psi to the engine fuel pump. This pump is mounted on the front of the accessory drive gearbox with a quick disconnect coupling. The fuel pump is a two-stage pump. The first stage is a centrifugal boost stage, which provides an initial fuel pressure rise. The pump delivers fuel to the fuel heater. From there, it goes to the fuel filter and pump main stage. The main stage of the pump is a positive displacement gear stage. It provides additional pressure rise and delivers the pressurized fuel to the fuel control. The main fuel filter is located within the fuel pump housing. It is a 40-micron paper filter and is replaceable at the line maintenance level. Mounted on the fuel pump housing is the fuel filter differential pressure switch. It activates whenever the pressure drop across the filter reaches 4.4 to 5.5 pounds of differential pressure. The fuel heater also mounts on the fuel pump housing. The purpose of the fuel heater is to prevent ice contamination of the fuel control. Should the filter differential pressure switch activate, it would illuminate a warning light on the flight deck. When this occurs, the fuel de-icing switch should be activated. Activation of the switch allows hot 13th stage compressor air to flow through the fuel heater. This heated fuel will de-ice the fuel filter. If the light stays on, it indicates another form of contamination has collected in the filter. However, if the light goes out, it indicates the flow restriction was caused by ice. The fuel control mounts on the front face of the fuel pump and is secured by washers and self-locking nuts. It is a hydromechanical control consisting of 2 major sections: the metering section and the computing section. Contained within the metering section is a fuel filter assembly, a throttle valve, and a minimum pressure and shutoff valve. The purpose of the metering section is to 1. Filter the fuel, utilizing a 2-element filter. 2. Meter the fuel through this throttle valve orifice. And 3. Turn the fuel on or off as controlled by the shutoff lever. The computing section determines the fuel schedule for all engine operating conditions, such as starting, accelerating, decelerating, and steady state. It does this by the integration of 8 input senses which combine to determine the throttle valve position. These 8 inputs are power lever position. This input is the pilot's request for thrust. N2 RPM, a mechanical input which is provided by the rotation of this shaft and is proportional to high-pressure compressor speed. PS4. This input represents the amount of air available for combustion. TT2. This temperature input biases the fuel flow schedule during engine idle and rapid accelerations. P-ambient. This ambient pressure input biases fuel flow schedules during approach and idle operation to ensure engine-supplied bleed air flow meets airframe pneumatic system requirements. Ground idle. This is the normal idle mode and is selected by energizing this solenoid. Ground idle mode provides low idle thrust to facilitate aircraft taxiing. Approach idle is the alternate idle mode. Placing the aircraft in the approach configuration de-energizes the idle solenoid, causing an increase in idle N2 RPM. This higher idle RPM setting ensures the engine can meet rapid acceleration requirements during approach and initial touchdown. The final input to the fuel control is the automatic reserve thrust signal, or ART signal, which, when generated, is sent to this solenoid. During takeoff, an aircraft onboard computer senses and compares the N1 RPM of both engines. If either engine experiences an N1 speed decrease, creating a 30% RPM difference, the computer energizes the automatic reserve thrust solenoid on both engines' fuel controls. The fuel controls schedule additional fuel, and the increased fuel flow causes a thrust increase on the engines. If necessary, this higher thrust setting can be achieved manually by advancing the throttle. There are only 2 line maintenance adjustments on the fuel control: idle trim and part power trim. These adjustments must be made periodically to maintain optimum engine operation. The fuel flow transmitter, which is normally located here, measures the fuel flow and sends this information to the fuel flow indicator on the flight deck. The fuel oil cooler is a core tube heat exchanger. The fuel flows through these tubes and cools the oil, which flows around the outside of the tubes. The fuel then flows on to the pressurizing and dump valve. The valve overboard dump port is plugged to meet environmental regulations. Now the component functions only as a fuel flow divider. During engine starting and idle operation, it supplies fuel to the primary fuel manifolds. As the engine is accelerated above idle, the valve allows fuel to flow to both the primary and secondary manifolds. An inlet fuel filter is located inside the pressurizing and dump valve housing. It must be periodically removed and inspected for contamination. The fuel flows through the external manifolds located under the engine, outside of the fan discharge diffuser duct. Internal manifolds then distribute the fuel to 9 of these fuel nozzles. Here, it is atomized and aerated for combustion. In review, the 9 major components in the fuel system are the fuel pump, fuel heater, fuel control, fuel flow transmitter, fuel oil cooler, pressurizing and dump or P&D valve, fuel manifolds and fuel nozzles, and the bleed valve control. The components which have filters requiring inspection are the fuel pump, the fuel control, and the pressurizing and dump valve. Now to review the flow path in schematic form. Fuel flows from the aircraft system to the main fuel pump and on to the centrifugal boost stage. The fuel then goes to the fuel heater. It then returns to the main stage of the pump where its pressure is increased. It then flows to the fuel control. Fuel not needed by the control is returned back to the main stage of the fuel pump. Fuel acting as a hydraulic signal called pressure deceleration bleed open is routed to the bleed valve control and back to the fuel control. From the fuel control, metered fuel is sent through the fuel flow transmitter and then passes through the fuel oil cooler. The fuel then goes through the pressurizing and dump valve. The fuel manifolds carry the fuel to the nozzles, where it is atomized and aerated for combustion. There are several safety features incorporated into the jt8d-200 series fuel system. For instance, should the centrifugal boost stage of the main pump fail to operate, fuel would bypass the boost stage, the fuel heater, and the main filter through a bypass valve set to operate at 0.5 to 1 pound of differential pressure and continue directly to the main stage of the fuel pump. This would ensure adequate fuel supply to the fuel control for proper engine operation. Should the fuel heater become clogged, the fuel heater bypass valve would open at 17 to 24 pounds of differential pressure and allow fuel to completely bypass the heater and go directly to the fuel pump. If ice crystals or contamination clog the main filter, the filter bypass will open at 8 to 10 pounds of differential pressure and ensure continued flow to the fuel control. Another protective measure located in the fuel pump is a high-pressure relief valve. When the pressure rise across the second stage of the fuel pump reaches 1,025 pounds per square inch, the relief valve begins to open. This prevents excess pressure from reaching the fuel control. The relief valve will be fully open when the discharge pressure rise reaches 1,040 pounds per square inch. The fuel control filter assembly has a bypass feature that operates at 15 pounds of differential pressure. The pressurizing and dump valve also has a filter. If it becomes contaminated, the filter will self-bypass at 10 to 12 pounds of differential pressure. This has been a brief description of the jt8d-200 series fuel system. The operation of this reliable engine is dependent on the proper operation of its fuel system.